What's up, team? Today we're going to talk about classifying triangles using the Pythagorean theorem. So we're going to classify right triangles, obtuse triangles, and acute triangles, all while using the Pythagorean theorem. So as a refresher, Pythagorean theorem says that c squared equals a squared plus b squared if and only if a triangle is a right triangle. C, of course, is the hypotenuse. It's the leg that's opposite of the 90-degree angle. A squared is one of the sides. B squared is another one of the sides. Doesn't matter which one's which because you're just adding them. So let's practice that with this triangle right here. Let's confirm that this is a right triangle. If we can say that 3 squared plus 4 squared equals 5 squared, then we can say that we definitely have a right triangle. So 3 squared plus 4 squared equals 5 squared. And I'm going to put a question mark over my equal sign because I don't know that it's true. I'm here to check it out. I'm here to explore. 3 squared is 9, 4 squared is 16, and 5 squared is 25. Well, 9 plus 16 is indeed 25. So 25 equals 25. This checks out. And what that tells us is not, we're not impressed that we found that 25 equals 25. We're impressed, or what we're interested in is the fact that c squared does indeed equal a squared plus b squared. Therefore, this is a right triangle. That's how we're going to be using the Pythagorean theorem in this particular lesson, and how we can use it to classify triangles. Okay, let's look at a second example. Here we have a triangle with side lengths of 8, 6, and 11. I've drawn it as a right triangle, but we don't actually know that that's the case. We're here to confirm that or see if there's something else we can see. So we're going to check, again, very similarly, we're going to do a squared plus b squared and see where this relationship is with c squared. So we're going to do 6 squared plus 8 squared, and then we're going to do our 11 squared. I purposely left this blank because we don't actually know that it's equal. We're just going to kind of see what we can see. We're going to treat this as an equation, but we're going to reserve the space for whatever symbol we'll end up using here shortly. Okay, 6 squared. 6 times 6 is 36. 8 times 8 is 64. 11 times 11 is 121. 36 plus 64, that happens to be 100, and 121 is still 121. I'm noticing that these two numbers are not equal. In fact, 100 is less than 121. So the major difference between these two figures, of course the numbers are slightly different, but the relationship between the numbers is here a squared plus b squared equals c squared. Here, a squared plus b squared is less than c squared. That means c squared is even bigger than the sum of a squared plus b squared. So if you think about our picture here, we have an a squared and a b squared. If c squared equaled their sum, it'd be a right triangle. But c squared is larger than what it needs to be for this to be a right triangle. That means that this, what would be a hypotenuse, is longer than what it would need to be if it were a right triangle. So that would end up opening up this angle even greater than 90 degrees. So if your a squared plus b squared, if that sum is less than your c squared, then you have an obtuse triangle. And again, the reason why it's obtuse is because if this relationship, a squared plus b squared equals c squared, it'd be a right triangle. In our case, the longest leg, what would be the hypotenuse, is greater than what it needs to be for a right triangle. So that means it's bigger than what it needs to be. So if this default is at 90 degrees and it's bigger, this angle would have to open up or stretch out and be greater than 90 degrees, making this an obtuse triangle. Let's look at a third example. We're going to check it the same exact way. We're going to check all of these the same exact way. So 7 squared plus 23 squared has some relationship with 24 squared. I don't know what it is. Could be more, could be less, could be exactly equal. That's what we're here to explore right now. I know that 7 times 7 is 49. I don't know what 23 times 23 is. My calculator says it's 529. 24 squared is 576. So now I'm going to add these two numbers together, 49 plus 529, and I get 578. Well, on this side, 576 is still the case. So now our sum of a squared plus b squared is greater than our c squared value. These ones are really close, but it's close isn't equal. So 578 is greater than 576. So it's kind of the opposite situation that we had over there. The correct number, if you will, or the hypotenuse is going to be slightly less than 24 if this was going to be a right triangle, if we wanted to force that to be the case. But since it's slightly greater than 24 to make these equal, yeah, slightly greater. So it's too small, meaning if it was a right triangle, the length that we have is a little bit smaller. So it's causing this, what would be a right angle again, it's causing it to shrink or to get a little bit smaller. So this would be an acute triangle because this angle cannot be a 90-degree angle. Acute triangle. So this is how you'd use the Pythagorean theorem to classify a right triangle is if a squared plus b squared equals c squared. An obtuse triangle, if a squared plus b squared is less than c squared, or an acute triangle, if a squared plus b squared is greater than c squared. Check page 2 of the notes that I posted there. It's painted out a little bit more clearly. Okay, one last thing, and this is kind of intuitive, but maybe you wouldn't see it if you don't see it. So let's say that we have a triangle with side lengths of 2 and 3 and 6. That doesn't sound weird at all. That just sounds like, okay, cool, 2, 3, and 6, fine. But let's explore the fact, is there any possibility for this to actually form a triangle? So I'm going to try to draw a triangle with side lengths of 2, of 3, and of 6. So I'll start here with my side length of 6, and then I'll draw a side length of 2, and then I'll draw a side length of 3, and notice that they are not touching. They cannot touch. Why? Well, we have one leg that has, or one side that has a length of 6, and the other two, if you add them together, they don't even make it to 6. Even if they are lying flat on the line, they would still be a unit shy of covering the whole distance there. So if you have 3 side lengths of a triangle, the 2 smaller ones must add up to something greater than the third side, than the largest side. They can't even be exactly the same. If I had 3, 3, and 6, I still can't make a triangle. But if I had 3, 3.01, and 6, technically I could. It wouldn't be a fun triangle to look at, but it could be a triangle. So this is loosely related to what we're talking about. Classifying triangles used in Pythagorean theorem. This one we're just kind of using a little bit of intuition, noticing, also we're not squaring anything. We're not even using Pythagorean theorem with this idea. It's just, is there any possibility we can have a triangle with side lengths 2, 3, and 6? No. If we had 2, 5, and 6, could we? Yeah, for sure, because 2 plus 5 is greater than 6. So that's just kind of a little bonus add-on to this particular lesson. Okay, Pythagorean theorem, classifying triangles. Dive into some practice problems. Let me know if you have questions. You got this.